Welcome to the SYCLcon presentation on backend interoperability. My name is Greg Luke. I'm from Intel Corporation and a member of the KHRONOS SYCL working group, but you'll hear also from several of my colleagues later in this presentation. Now, before we can understand what the SYCL backend interoperability mode is, we need to first understand what a SYCL backend is. This diagram shows a SYCL application running on top of a typical implementation of SYCL. The top box is the SYCL application. This is just a C++ program that calls the SYCL APIs. Underneath that is the runtime library. Every SYCL implementation provides this. This is an implementation of all those APIs that your application calls. Now, most implementations of SYCL don't implement the parallelism directly. They instead translate the SYCL level parallelism into calls to some existing parallel framework. For example, OpenCL, Level 0, HIP, CUDA, possibly something else. These frameworks are what we call the backends in SYCL, and it's those backends that expose the offload devices. It's important to realize that not every SYCL implementation will support every possible backend, though. Most SYCL implementations provide only a subset. It's even theoretically possible that a SYCL implementation could layer directly on the hardware without using any backend. But most existing SYCL implementations do support a subset of the backends shown here. Now that we understand what the SYCL backend is, we can ask what the backend interoperability is. Well, the concept is fairly simple. Let's say that you know that your SYCL implementation uses a particular backend. For example, OpenCL is shown in this diagram. Well, you may ask yourself, if I know that everything is running on OpenCL anyways, why can't I intersperse some OpenCL calls along with all my SYCL calls? And the answer is that you can. That's exactly what the backend interoperability does. It provides a way for you to intersperse backend specific calls with your SYCL calls and a way to relate the two APIs together. Now, there are several reasons why you might want to use backend interoperability. The first is that you may start with some application that's already written in some backend. For example, maybe you have an OpenCL application, and you want to take that application and you want to either port part of it or augment part of it to use SYCL. Doing this would result in an application that's a mixture of both the backend calls and the SYCL calls, and the backend interoperability provides a way to do this. Another possible use case is sort of the opposite. You may already have a SYCL application, but you might need to call maybe a third-party library that is backend specific. So in order to do this, again, you can use the backend interoperability in SYCL. The third reason that you might want to use the backend interoperability is to take advantage of some backend specific features, and we have an example of that later. Now, it's important to realize that even though backend interoperability gives you some advantages, there's also one big disadvantage. It reduces the portability of your application. Once you start coding to a particular backend, your application is only going to run on a SYCL implementation that also supports that backend. So although that you get some more power with these backend interoperability APIs, you also have the disadvantage of losing some portability. There are three main types of backend interoperability, which I demonstrate in the next few slides. The first type allows you to get a SYCL object from a backend object. To illustrate, let's take a look at this OpenCL function, which takes a CL device ID as a parameter. The goal is to submit some work to this device using SYCL APIs, but in order to do that, we need to somehow get a SYCL device that corresponds to that OpenCL device ID. The makeDevice interoperability function provides that ability. MakeDevice is a templated function where the template parameter is an enumeration indicating the backend, and the function parameter is the OpenCL device ID. The return value from MakeDevice is the SYCL device object. Once you have the device object, you can then use normal SYCL APIs to submit work to it. So for example, here, we create a SYCL queue on top of that device, and then we submit a parallel for kernel to the queue. In addition to MakeDevice, there are similar APIs for creating other SYCL objects from their associated backend objects. For example, there's a way to create a SYCL queue from an OpenCL queue, etc. The typical use case here is when you have an existing application that's already written using a backend APIs, and you want to add new functionality to that application using SYCL APIs. The second type of backend interop allows you to get a backend object from a SYCL object, sort of the opposite of what we saw before. To illustrate, let's take a look at this code snippet where the function takes a SYCL device object as a parameter. The goal is to use OpenCL with that device, but in order to do that, we need to somehow get a CL device ID that corresponds to it. The interop function getNative provides a way to do this. GetNative is again a templated function where the template parameter identifies the backend, and the function parameter in this case is the SYCL device object, and the return value is the corresponding SYCL device ID. Once you have the device ID, you can use any of the normal OpenCL APIs on that device. So for example, here we illustrate calling CL get device info to enumerate the built-in kernels. And you can imagine that there might be other code later that invokes one of those built-in kernels. GetNative here is shown with the SYCL device object, but there are also overloads of GetNative that work with most of the other SYCL objects. So for example, you can get an OpenCL queue from a SYCL queue, etc. There are two main use cases for this type of backend interop. In one case, you have a SYCL application where you need to call a backend specific library. And in the other case, you may have a SYCL application and want to make use of some backend specific feature, like the built-in kernels we illustrate here. The last thing I want to point out on this slide is the use of the SYCL backend OpenCL macro. As I mentioned earlier, an implementation of SYCL may not support all backends, and this can reduce your code portability if you use these backend interop. You can regain some of that portability, though, by enclosing your backend specific code in an if-def like this. However, then you need to have an else clause with some fallback code in case the implementation doesn't support your particular backend. The third type of backend interop is similar to what we saw in the previous slide, except that instead of calling the backend APIs synchronously from the main part of the application, we instead call them asynchronously as part of the dependency graph. To illustrate, let's take a look at this function, which takes two parameters. One is the SYCL queue, and the second is a SYCL buffer. We submit a task to the queue, but rather than submitting a kernel like a parallel 4 kernel, we submit a host task. Notice that we call the host task member function of handler rather than calling the parallel 4 member function. A host task is just a regular C++ function, except that SYCL executes that function according to the dependency graph. Dependencies are set up using accessors just like they are with kernels, so you can see here that we create an accessor on top of the buffer, and then we reference that accessor from inside the host task. The interoperability part comes from the special interop handle that's passed as a parameter to the host task. The interop handle allows you to get the associated backend object from an accessor. So here we call getNativeMem, pass the accessor as a parameter, and we get back a CLMem object. You can then use the CLMem to reference any data on the device that's inside this buffer. Now the slides I've shown so far are just an introduction to the backend interop APIs. I'm going to hand the presentation off now to Gordon Brown from CodePlay, who's going to go into some more detail and also present some specific use cases.
Hello, my name is Gordon Brown. I work at CodePlay and I'm going to talk to you about host tasks, specifically the interoperability capabilities of host tasks. And then I'm going to show some real-world examples of where this functionality is used to interoperate with backend specific libraries. The host task allows you to enqueue arbitrary C++ code asynchronously within the SYCL dependency graph. As this is regular host C++ code, the restrictions you would normally associate with kernel functions doesn't apply here. However, all the same dependency graph rules which apply to SYCL kernel functions, for example when using parallel for, also apply here. To enqueue a host task, you simply call the host task member function on the handler object. The standard host task will execute the function on the host and will make the data for any accessors available on the host. In this example, we retrieve the pointer from an accessor and call a regular C++ library function with it. If there were to be a SYCL kernel function before and after the host task in the DAG, the data would be copied back to the host for the host task to execute and then copied back to the device again afterwards. The other thing to note here is that host task functions must be self-contained, which means all work performed within a host task must be completed before the function returns. This is particularly important when using host task interop, as we'll see in a moment. As we saw earlier, host task also provides some interoperability capabilities. To access these, you simply call the host task function with the optional interop handle parameter. Using the interop handle parameter instructs the SYCL runtime that the host task function will be enqueuing commands to the native backend API. The function still executes on the host, however, now the data for any accessors is made available on the device instead of the host. Commands can then be enqueued to the native backend API to execute on that device and access the data using native backend objects. These objects are retrieved by calling member functions of the interop handle object. In this example, we are interoperating with the CUDA backend. So we retrieve the native CUDA stream for a queue via getNativeQueue, and then we retrieve the native CUDA pointer for an accessor by calling getNativeMem. We then call some CUDA library, passing in that stream and pointer. If there were to be a SYCL kernel function enqueued before and then after the host task, in this case the data would remain on the device as the host task is interoperating with the native memory objects for that device. Again, as with the standard host task, the host task function must be self-contained. For interop, this means that no asynchronous commands can be enqueued without also waiting for those to complete. One final point, the native backend objects returned are relating to the internal SYCL runtime state at the point in the dependency graph that the host task is being executed. So this means the host task function is called dependencies have already been resolved. Now I'm going to show some real-world examples where the host task interop is being used. The oneAPI projects, oneDNN and oneMKL. The oneDNN project is using host task interop for calling native DNN libraries, and similarly the oneMKL project is using the host task interop for calling native BLAS and RAND libraries. There are links to these projects if you want to check them out. For the Nvidia backend of these projects, they map to the CUDA libraries QBLAS, QRAND, QSolver, and QDNN. Each of the operations provided by the oneDNN and oneMKL libraries maps to a host task executing the equivalent library function in the backend library. Each of these operations also supports both the buffer and accessor and USM memory management models. As the host task is executed within the SYCL dependency graph, the operations are automatically composable. This allows the oneAPI libraries, which are written in SYCL, to take advantage of these existing well-optimized libraries for the various backends that it supports, in this case Nvidia GPUs. Finally, here's an example of what this looks like from the oneDNN project. This is part of the code from one of the convolution operations in oneDNN which maps to QDNN. Here, a host task is enqueued from the interop handle and is used to retrieve the CUDA stream and a number of native CUDA pointers. These are then passed to a function which invokes the QDNN library functions with those. So in conclusion, the host task interoperability is useful in cases where you have a SYCL application and you wish to call native backend APIs or libraries from within it. This could be any backend such as OpenCL, OpenMP, CUDA, HIP, Level 0, or any other. The backend interoperability within a host task provides access to the native queue, event, and memory objects, and the host task is enqueued within the data dependency graph of the SYCL runtime, so it synchronizes with other SYCL kernels. I'll now pass over to Thomas Applincourt of Oregon National Labs, who's going to talk about interoperability between SYCL and OpenMP.
Hi, my name is Thomas Applincourt and I work at Oregon National Lab. Today I want to talk to you about OpenMP and SYCL and the interoperability between the two. In HPC, the majority of applications are using OpenMP, but some applications may want to be interfaced with SYCL. For example, for some libraries, the SYCL API are more rich than their OpenMP counterpart. One example is the oneMKL library, who provide both an OpenMP and a SYCL API. But the SYCL API gives us more flexibility, it gives us more access to some function. For example, batch gem is only available in the SYCL API. Also, some library can only provide a SYCL API and not an OpenMP API. For example, below I will show an example using oneDPL, who is a parallel STL implementation of Intel using SYCL. Thankfully, we can interop OpenMP and SYCL. For example, at the bottom, I show you a little code snippet who run at the moment, where I allocate some memory, I map some memory using OpenMP. Then I do some OpenMP trickery to be able to get the host pointer, the device pointer associated to this host pointer. Then I create an interop queue. I will discuss more about this function in the next slide. And then at the end, you see we can use std sort with the parallel executor using the SYCL queue and data who was allocated using the OpenMP runtime. So how does this work? The trick is to use a middleman to use native handler. So for example, you can use OpenMP level 0 SYCL, OpenMP CUDA SYCL. How it's worked is to go from the OpenMP to the native handler, you use the newly introduced Pragma OpenMP interop, who is coming from OpenMP 5.1. Then from this handler, you can create some SYCL object using SYCL 2020 function. We have a proof of concept implementation in the repo below using level 0 as the middleman and ICPX as the OpenMP and SYCL compiler. I will not go deep into the detail, you can look at the code. I think the only major trick is to be sure that SYCL and OpenMP are using the same context, the same memory context. So both can be interop without any problem. Below, I show you a little code snippet, how it works internally. And after you can maybe look at the main code if you want to have more details. But the code is exactly as I explained before. You start by creating this interop object. Then after you pass in the Pragma OpenMP interop init, this will give you access to initializing this interop object. Then you can use the OpenMP getInterop pointer function. In this case, we ask for the native handler of the device that we cast into a level 0 handle. So now we have a level 0 device handle that we can use in this SYCL make device function to be able to create a SYCL device. So in the main code, we do that for everything, for the context, the queue, and everything. And at the end, you can get a queue who is interop. We can be used as an interop between OpenMP and SYCL. And it works. For example, in this example, I can use a memory who will be mapped using OpenMP and a memory we've been allocating in SYCL, and I can use that inside an OpenMP target region. So I have this interop between OpenMP and SYCL, where inside an OpenMP region, I can use SYCL. And later I have the opposite, where inside a SYCL function, here q.copy, I can use some memory who have been allocated using the OpenMP API. It's not perfect yet. So it's right now, as you saw in the previous slide, is backend specific. You need to have some cast and you need to specialize the template and everything. In fact, we only tested it for ICPX and level 0. And to be totally honest, to be totally transparent, right now we need to work around some bugs. So if you look at the code, you will have some ifs there for using non-standard interoperability API. but this should be extended and it is just temporary workaround. We are welcome to get any more implementation, to start in collaboration for testing, for maybe developing a better API. So please don't hesitate to ping me if you want to participate in this project. Thank you very much.
Hello, my name is Ronan Carriel. I am with AMD and I'm also the spec editor for the KHRONOS SYCL specification. If we have this SYCL interoperability layer, we can actually use it as a higher level API for all the native API behind the various backends. And then it will provide you a modern C++ cool SYCL interface with all the usual SYCL features. And what is also interesting is that you will be able to mix and match in the same program various code from the various native APIs. Obviously, there are already plenty of C++ wrappers targeting these native APIs, such as OpenCL, but with SYCL, you could have just one high-level wrapper to rule them all in the same application. And then you will just have one to learn. But it's important to note that in that case, it's no longer a normal single source SYCL program you will have, because you will have also various device programs in another source code. For example, we can start with simple OpenCL program, which includes an OpenCL C code in the middle, among a lot of OpenCL C API. So at the end, you will have something like 142 lines of code. But we can rewrite this OpenCL program by replacing most of the C host API by SYCL code. So the program becomes more like a simple program. So we will have some SYCL buffers, and we will initialize the data from the host by using host accessors. And then we want to create our vector addition OpenCL code that we will put in some arrays of strings. And to compile this OpenCL C code with the C API, we need to get some OpenCL context here. And from this, we can compile with the CL create program with source from OpenCL, our kernel code. Then we can build the program, and we can extract the kernel with the SYCL create kernel OpenCL API, and build again a SYCL kernel here. And then when we have that, we can use the SYCL interoperability mode to attach all our accessors to the OpenCL C argument in the same order. And then we can just call our kernel here with a parallel for with an explicit call on the kernel K. And at the end, we can just get back the data to our to the host and to check that the computation is correct. But what you can see is that we've used only the minimum OpenCL C API to build our kernels, and all the data motions between the host and the device and the graph, dependency graph, is done by using SYCL, so you do not have to worry about when and how to do the data transfers. But what is interesting is that we can redo the same with a completely different API. For example, in an FPGA context, I can start with an HLS C++ application where you have a specific vector edition and an XRT C++ host code, and the kernel is defined with some C++ API plus some pragmas to specify how you want to organize your data transfer. I don't want to enter into the details, but behind the scene you have 4 different functions interacting through FPGA streams. By using the SYCL interoperability mode, we can build from scratch a higher level XRT, which allows you to divide by mostly 2 the number of lines required compared to plain XRT C++ code. So in a similar way to the OpenCL example we showed before, we can just initialize our SYCL buffers on the host, then we will get the XRT device behind our SYCL queue. We will load some already built FPGA bitstream, extract the vector, add into the XRT kernel. From that, we will build back our SYCL kernel. Then we can, with the interoperability API, we can set the arguments of our kernel from all the accessors and the size of the data, and we will call our kernel with a single task. And at the end, we will just verify the result. So what is interesting to see is that nowhere we have expressed explicit data transfers compared to the initial XRT program. So it's really show that it can simplify the code. So to conclude this presentation, SYCL is an open standard for high-level heterogeneous accelerator programming. It can really target a broad range of architectures with different backends from various vendors. A normal SYCL program is a single source C++, and it can target various native APIs. So there are different backends which are used behind the scene transparently, and there is no need for explicit interoperability mode for usual cases. But for more complex cases, using explicit interoperability features of SYCL is really the key for the openness of this standard. In one direction, SYCL can use specific features of different backends at the same time. In the other direction, SYCL can be used from other heterogeneous programming frameworks. And if you combine these both features, for example, you can use SYCL as a single unifying high-level C++ wrappers for all the lower level APIs, and it will bring you asynchronous execution, task graph, automatic data transfers, and computation overlap, and so on. So thank you for your attention.